Hello, I hope everyone is having a great day when they start watching our video. Today we're going to be talking about net force, but before we get into all the details of net force, I wanted just to do a quick review on Newton's laws. So, for Newton's laws, the first question, I encourage you guys to pause the video and think about this is, do you remember what was Newton's very first law? So what did we say his first law is? Said his first law is that an object in motion will stay in motion unless acted upon by an unbalanced force. And then, do you remember we showed a video to kind of demonstrate this? And that video was a coin dropping into a cup or an egg falling into water. We had something resting, we had a piece of paper and a coin resting on that piece of paper on top of a cup, and if we pulled the paper out, the coin fell because our object at rest, being our coin, wanted to fall through and stay at rest. Alright, what is Newton's second law? Again, I encourage you guys to pause the video and think. Newton's second law is force is equal to mass times acceleration. And a demo that we showed for this one is that we had two cans rolling down a ramp. We had one that was full and one that was empty. And the one that was full, that had more mass, went faster. It had more acceleration. And then finally, Newton's third law is that every action has an equal and opposite reaction. And what demo did we do for this? Well, we showed a video about a balloon, or I encourage you guys to do balloon cars as well. The fact though is if we let go of our balloon, that it will go flying in the opposite direction. So our action is the air pushing out of the balloon, our reaction is the balloon going forward. So now to get to net force today, again, some more questions to get you guys thinking. What are types of forces you may know already? Some of the things I've heard already are friction and gravity seem to be common ones that we already know, but maybe you guys know more. And then when something is at rest, what force are the forces balanced or unbalanced? So right now, maybe you have your desk that is not moving. Would you say those forces around it are balanced or unbalanced? We're going to be talking about that today. Of course, they are balanced. If something's not moving, they're balanced. If something is moving, something's unbalanced. And then our last question to get us started is just the opposite. When something is in motion, are the forces balanced or unbalanced? Well, they're unbalanced. If something's moving, it's unbalanced. If something's at rest, our forces are balanced. So by the end of today, we want to be able to understand applied, gravitational, normal, and friction force. So we're going to learn about 4 different types of forces. And then we're also going to learn how to calculate basic net force problems. So please pause my video and go watch this video. It does a good job explaining what net force is. It's a short video, only a couple minutes long, and it does a good job explaining these different types too. So we have 4 main types of forces we're going to learn about. The first one we're going to learn about is applied force. So applied force is the force put on an object. So this can be in any direction. We have a couple pictures here. We have this person pushing this block. We can see the applied force is this arrow in which the direction is pushing. Or this person pushing a cart, and the applied force is in the force of that is getting pushed. This can be in any direction. If I want to put a force upward, maybe I'm pushing something above my head. I could be pushing something down. It can be in any direction. Some good examples, like we can see, is pushing a box, maybe even pulling a rope. We can apply a force on something by pulling a rope as well. So that's applied force is number 1. Number 2 is gravitational force. So that's also known as gravity, but it's the force from gravity or gravitational force. They both have the same start, gravity, gravitational. And this is always going down toward the center of the Earth, on Earth. If we're in space, it's a little bit different, but we're going to only be working on Earth. So it's always going towards the center of the Earth. We can see all of these arrows pointing towards the center of the Earth. On our picture up here, gravity is going to mainly be pushing down. So gravity is always pushing us down. It's the reason why we're not floating in air or doing anything like that. So some examples when we see gravitational force is things fall when they drop them. If I were to let go of my pencil off the desk, it would fall because of gravity. And then also everything. So everything we see all around the world experiences this gravitational force. All right, our next type is a normal force. So this is the force perpendicular to the surface on an object. So perpendicular means it's like a 90-degree angle from the surface. So we can see, it also opposes gravitational force. So we can see here on this top one, perpendicular to this surface, a 90-degree angle from this surface is just straight back up, and it opposes gravity. So gravity is pushing down. The normal force is going to push up against it. And we can also see on this incline that perpendicular means this 90-degree. So instead of going straight down, gravity is going down, but the normal force is perpendicular to the surface. So it's 90 degrees from this slope that we have here. This normal force is the reason why things are at rest. So if we were thinking about our desk is a good example. If our desk was experiencing gravity and only had this arrow, this gravity arrow down, that means it would keep going down. That means it would be unbalanced. And so it would start moving towards the center of the earth and going all the way until the center. But obviously we know our desk is not moving. And that's because this normal force is the opposite of our gravity. So it will cancel them out. It will cancel out our gravity, so we're at rest. Oh, perpendicular, it's 90 degrees from the surface. This is different on a slope, and it can get very complicated. So we're not going to focus too much on slopes yet. We need some more math skills that we haven't learned yet to focus on how to calculate that with a slope. And so we'll just worry about things on flat surfaces. But an example is a box on a table or a rock on a hill. Maybe this is more of a rock. But a normal force is just like gravity. Everything experiences it because it has to oppose gravity. All right, our last one we're going to learn about is friction. So friction is the force opposite of object's movement, or a force that opposes an object's movement. So some examples here are a ball rolling in grass or a box sliding along the ground. We can see that in our pictures we have our applied force going to the right. So our friction force, if our box is moving to the right, our friction force is going to be in the opposite direction, trying to slow us down. We can see it in this box too. We have someone pulling on a rope with their applied force. The friction is the opposite. And we can even see on this incline, this box wants to go down the incline, but this F stands for friction that opposes it. So friction is the thing that keeps, that slows objects down, that gets them to stop. If we didn't have friction, when we kicked a soccer ball, it would never stop. It would roll forever and ever and ever. So this is what slows objects down or keeps them from moving. It opposes motion. It's the opposite of motion. So we're going to learn what net force means. So net force is the sum of all the forces. So we can draw nice little boxes as our diagrams and then put different forces on them to explain how it's being affected. So for example, if we have opposite directions, so forces in opposite directions like our normal force here and our gravitational force here, we're going to subtract them. So the net force is the sum. So it would be like saying we're going to take 50 minus 50. So we would have 0. Our net force for our gravity and our norm is going to be 0. If we're in the same direction, which happens sometimes, like here we have 2 arrows for this FR, we would add them together. Up here we don't have any in the same direction, but if they're both going up, for whatever reason we have 2 forces forcing something up, we would add them. This gets really complicated with hills, slopes, or angles. Like we can see down here, we need what is called trigonometry, or trig functions, and so we're not going to get into that right now. We're going to stick to just some of the simpler ones. But I have this very good simulation to help us picture and see some net forces. So once it loads, hopefully it will work for us. It's taking a second. But this idea of net force, I think, as it loads, is a easy one once we get our heads around it. I think it can be kind of hard to understand at first, but once we get it, I think it'll be easy. I'm going to keep going here. Give that a second to load. So what we're going to look at is some examples of solving for the net force. So in this picture, we have something that says our net force is 0. So that means that everything on the right is equal to the left, so anything pulling to the right is the same force pulling to the left, and anything pulling down is the same force pulling up. So because we have a 0, we need to make sure that everything cancels. So our first question is, what would the force of A be? Well, we need it to be the exact same as the force pulling to the right, so it'll be 50 newtons to the left. A is going to be 50 newtons to the left. And we have the same question for B. What is the force of B going to be? Well, if we have 200 newtons pulling down, we need 200 newtons pulling up because our net force, or F net force, is 0. So let's check on our loading. Oh no. Alright, let's refresh it. Maybe that will help. Alright, let's go to the next one, just while that loads. Alright, so we have another one. This one only has one arrow, or actually I should say 2 arrows, one arrow that we need to find. So this question is, if our force net, or net force I should say, has 90 newtons up, we have 90 newtons going up, what is C going to be? Well, if we put 900 newtons right here, then our net force would be 900 minus 200, because we have to subtract them because they are in opposite directions. So another way to do this, I kind of made a nice little equation here. Sometimes people can just do this without an equation. Some people, like me, need equations to help us. But some of us intuitively, or just looking at it, can notice that we're going to need 1,100 newtons. And the reason is, if we have our F net is equal to our C minus our 200, we're going to need to do 900 is equal to C minus 200. Well, to solve for C, we would add 200 to the other side to get 1,100 newtons up. Some of us can just sit here and look and say, if C is 1,100 and we subtract 200, we get 900. But if you're like me, I like to do some equations like this. So let's check on our simulation again. If this isn't going to load for me now, I'll post a link about it in our classroom and have you guys check it out. Or I might make another video. Alright, let's go back to our PowerPoint here, get through. I'll have to make another video about that. So we have the next one about E and D. So this says our net force is going 60 newtons to the left. So we're going to have an unbalanced force moving us to the left. So that means that we aren't going to move up or down. So our E needs to be the same as our force pulling us up, because our E pushes us down. So we're going to have 300 newtons down. And then our force to the right needs to be less than 80. We need to go to the left by 60 newtons. So if our F net is equal to, this should be D minus 80, and our F net is 20 to the left. Oh, I messed that up. I'm sorry. So what we should have is that our D should have 20 newtons, because we want to end up going 60 newtons to the left. So if D is 20 newtons, then it would push us to the left by by 60. So we are just finishing up on our time limit for our video. I'm going to make another one with our simulation to have us continue on.